A trip to Mars today takes 7 to 9 months, and NASA's own studies confirm a nuclear thermal rocket could cut that to 3 or 4. The science has been tested and proven on the ground since the 1960s. I was reading a January 2026 MIT report modeling a complete nuclear rocket engine, every pump, every tank, every pressure curve, and what struck me was not the ambition. These are not sketches. They are full engineering simulations ready to be built. The only thing that ever slowed this down was decisions, not science. What the headlines are not telling you. The science of nuclear thermal propulsion is not theoretical, it is proven. NASA's NERVA program ran full-scale ground tests in the 1960s and achieved 825 seconds of specific impulse. Today we break down exactly how it works, why it is twice as efficient as any chemical rocket ever built, and what the latest 2025 research from Ohio State says about pushing that even further. Welcome back to Tomorrow's Science. Let's dive in. Chemical rockets. Every rocket ever launched to Mars worked by burning fuel and oxidizer to produce thrust. The fastest mission to Mars ever took over 6 months, and it carried no crew. Every day astronauts spend in deep space. They absorb cosmic radiation at levels far beyond what is safe long-term. The shorter the trip, the lower the total dose, and that is the central medical challenge of any crewed Mars mission. 7 to 9 months of microgravity causes documented bone loss, muscle atrophy, and cardiovascular changes, all confirmed by NASA's ISS studies. Cutting transit time in half directly reduces every one of these health risks. A nuclear thermal rocket does not carry a weapon and produces no explosion. It uses a compact fission reactor, the same physics used in nuclear power stations, to generate intense heat transferred to a liquid propellant. That superheated hydrogen, heated to around 2,700 degrees Kelvin, expands and exits through a nozzle to produce thrust. No combustion, no burning fuel and oxidizer, just thermal energy from fission driving propellant at extreme velocity. The U.S. Department of Energy confirmed it clearly. Chemical rockets achieve around 450 seconds of specific impulse. A nuclear thermal rocket targets 900 seconds, exactly twice as efficient. That gap is what changes the Mars equation entirely. Between 1959 and 1972, NASA ran the NERVA program, Nuclear Engine for Rocket Vehicle Application. Engineers built and tested full-size, flight-ready nuclear rocket engines on the ground in Nevada. These were not scale models. NERVA achieved 825 seconds of specific impulse and ran engines continuously for over an hour. Engineers deliberately pushed engines past design limits to study failure, and the engines remained controllable throughout every test. The program was canceled in 1972 due to budget cuts, not because it failed. The engines worked. NASA's own records confirm NERVA proved nuclear thermal rockets function in practice, not just on paper. Specific impulse is the single most important number in rocket engineering. It measures how much thrust an engine produces per unit of propellant consumed. The higher the number, the farther you travel on the same amount of fuel. Chemical rockets produce heavy water vapor exhaust, which limits exit velocity. Nuclear engines use pure hydrogen, the lightest element heated to far higher temperatures. Lighter gas plus higher heat equals far faster exhaust and double the efficiency. According to IEEE Spectrum's analysis of the DRACO program, Lockheed Martin's nuclear engine targets 700 to 900 seconds of specific impulse, compared to chemical rockets at around 400. That efficiency difference is what cuts the Mars trip from 9 months to 4. In January 2023, NASA and DARPA officially announced DRACO demonstration rocket for Agile cislunar operations. Lockheed Martin was selected as prime contractor, with BWX Technologies developing the reactor and its high-assay, low-enriched uranium fuel. The DRACO spacecraft was designed to operate in a high orbit between 700 and 2,000 kilometers above Earth, safely away from inhabited orbits. The reactor would only be switched on once the spacecraft reached that safe altitude. In June 2025, NASA's fiscal 2026 budget request canceled DRACO's funding. This was a budget decision, not a technical failure. The engine designs, fuel specifications, and full engineering data from the program remain documented and available. While DRACO wound down, researchers at Ohio State University and the University of Alabama at Huntsville published findings in the journal Acta Astronautica in May 2025, introducing the Centrifugal Nuclear Thermal Rocket, or CNTR. The research team calculated the CNTR could enable a complete round trip to Mars within a single year. This is a peer-reviewed paper in Acta Astronautica, with engineering calculations from 2 U.S. research universities, not a press release. In January 2026, MIT researchers completed the most comprehensive simulation of a complete nuclear thermal rocket engine ever attempted, modeling every component simultaneously: tanks, pumps, reactor core, nozzle, and all pressure-temperature interactions between them. The simulation mapped exactly how the engine behaves during startup and shutdown, when temperature and pressure swing by thousands of degrees within seconds. Understanding this precisely is what allows engineers to design the engine to handle those moments safely. The MIT work confirmed what NERVA showed in the 1960s. The physics is sound, the engineering is solvable, and the gap between simulation and hardware is narrowing. The question is no longer whether it works. It is when the funding and mission commitment arrive. Deep space between Earth and Mars contains 2 radiation types with no equivalent on Earth: galactic cosmic rays streaming in from outside the solar system, and solar energetic particles released in unpredictable bursts. Neither can be fully shielded against with current materials. NASA's published health standards set a career radiation limit for astronauts. A 9-month one-way chemical trip to Mars would consume a significant portion of that entire career limit in a single journey. A 4-month nuclear trip cuts that exposure almost in half, just by spending less time in the radiation environment. NASA engineers and space medicine researchers consistently make this point in peer-reviewed literature. Reducing transit time is not about speed or comfort. It is the primary medical strategy for protecting crew health on a Mars mission. Propulsion and medicine are the same problem. Mars launch windows, when Earth and Mars align closely enough for an efficient trajectory, occur only once every 26 months. Miss one on a chemical rocket and you wait over 2 years. The window is also narrow, a few weeks at most. As IEEE Spectrum's DRACO analysis noted, a faster rocket widens those windows, shortens trip duration, and reduces time-sensitive constraints on both cargo and crew. Nuclear thermal propulsion gives mission planners far more flexibility in scheduling departures and returns. In a crewed mission where emergency evacuation might be necessary, that flexibility becomes life-critical. Chemical rockets are so constrained by orbital mechanics that an emergency return from Mars is essentially impossible outside specific windows. A nuclear rocket opens more options. The legitimate safety concern with nuclear thermal rockets is not operation in space. It is the launch phase. If a chemical rocket carrying a nuclear engine fails during ascent, radioactive material could be released. The DRACO program addressed this directly in its design. The solution is direct. The nuclear reactor is not activated until the spacecraft reaches safe high orbit, carried there by a conventional chemical upper stage. The HALEU fuel used in DRACO is low-enriched uranium, the same category used in commercial nuclear power reactors, not weapons-grade material. NASA's NERVA program conducted over 20 ground tests without major incident, including deliberate overpressure and failure tests. The U.S. Department of Energy has publicly stated that NTP technology has a documented safety record from the 1960s that supports its feasibility for space use. As of 2026, DRACO has been defunded, but the engineering data from Lockheed Martin and BWX Technologies remains fully documented. The University of Florida, under NASA's Innovative Advanced Concepts program, is actively researching a bimodal nuclear engine that researchers calculate could reach Mars in 45 days. Ohio State's CNTR research continues with active funding in 2025. Researchers at Georgia Institute of Technology are running reactor core simulations studying how the engine manages extreme startup and shutdown cycles. The key remaining engineering challenge before hardware can be built. Multiple independent research groups across the U.S. are converging on the same conclusion NERVA reached in 1972. Nuclear thermal propulsion works, and it is the most practical path to a crewed Mars mission within a reasonable time frame. The case for nuclear thermal propulsion is not built on hope. It is built on 50 years of documented engineering. The physics was proven in Nevada in the 1960s. The efficiency numbers are confirmed by the U.S. Department of Energy, and the health argument is backed by NASA's own space medicine research. Canceling DRACO in 2025 was a budget decision, not a scientific verdict. Research continues at Ohio State, Georgia Tech, MIT, and the University of Florida. The engineering knowledge is not lost. It is waiting for the next commitment that matches the scale of the problem. Every credible long-duration crewed Mars mission architecture in NASA's published literature includes nuclear propulsion as the preferred or required solution. The science is ready. That is tomorrow's science, and it has been ready far longer than most people realize.